Hello and welcome to this lecture on fundamental of electric drives. Now, in the last lecture we were discussing about the equivalent drive parameters when we have a gear in between the motor and the load. So, we have seen here that when we have this motor and the load and we have this gear here, this equivalent parameters, for example, the inertia appears as J naught plus J 1 A 1 square, and the torque which is seen by the motor appears as T L naught plus T L 1 by eta 1 into A 1. A 1 is the gear ratio. A 1 is equal to N by N 1, the ratio of the teeth, that is equal to gear ratio. Now, this is the case of the rotational system. So, this is the rotational load. When the road is rotating. So, when we have more than one gear, we see that we have the gear ratio as A 1, A 2 and so on. The effective inertia seen by the motor is J naught plus A 1 J 1 square plus A 2 J 2 square plus A 3 J 3 square and so on. And similarly, the equivalent load torque is equal to T L naught plus A 1 T L 1 by eta 1, eta 1 is the efficiency of gear 1 plus A 2 T L 2 by eta 2 and so on. So, these are the various terms, and if you have more than one gears, we have more than one terms, and this can be extended to n number of gears. Now, we also have translational system. What do we mean by translational system? The translational system does not rotate, it basically goes in a linear motion. Say for example, a lift is going up and going down, that is a translational motion, but behind this there is a motor. So, there is a conversion between the rotational motion to translational motion. Now, we will see the coupling of a translational load with the motor which is rotating. So, we will be discussing right now about the translational load. Now, in this case we have a motor which is coupled to a load this is load 0, let us say, and this is a mechanical coupling. So, load 0 is a rotational load. Then what we have? We have a conversion system which convert rotational to linear motion transmission. And then what we have here? We have a mass here which is a mass which is going down or going up at a velocity v 1, and this mass is having m 1 and this is exerting a force here, force is F 1. And the motor and the load combination has an effective inertia of J naught, the first load, that is the 0th load, and the motor is rotating at a speed of omega m. The load 0 is opposing this with a load torque of T L naught. Motor torque here is TL. So, we have to find out what is this effective TL, and the linear velocity of this mass is V1. Now, in this case we will apply the same method here. We will first find out the effective kinetic energy of the system. Here we have a rotational system which is rotating, that is the load 0, and we have a translational system which is going up or down, which is in a linear motion. So, what is the effective kinetic energy of the entire system? So, the kinetic energy of the entire system, let us say equivalently we have the equivalent inertia j, and the equivalent speed is omega m square, omega m. So, the equivalent kinetic energy is half j omega m square, that is equal to the kinetic energy of the first load, that is half j naught omega m square plus kinetic energy of the second load. The second load is a translational load, that is half m into V1 square, half mv square is the kinetic energy of a translational load. So, this is the effective kinetic energy of the system. So, if you want to find out the effective inertia is j, that is equal to j naught into omega m square by omega m square plus m V1 square by omega m square. We can simplify that, that is equal to j naught plus the mass of the translational load into V1 by omega m square. So, this is the effective inertia seen by the motor. So, we have a translational load that is having the motion, and that velocity is V1. So, the ratio of V1 by omega m square is used for transforming the mass into the rotational mass, that is the moment of inertia. So, it is j equal to j naught here, that is the original moment of inertia. The added one, because the translational load is this part, that is m into V1 by omega m square. Now, what about the effective load torque? Now, if you want to see the effective load torque, we have to see the power seen by the motor. So, the power seen by the motor is TL into omega m. Now, this power consists of the power of the load 0, that is TL naught into omega m, and the power of the translational load, the power here is force F1 into the velocity V1, that is the power force into the velocity, but this is having a coupling efficiency is eta 1, eta 1 is the coupling efficiency. So, we have to divide by the coupling efficiency, that is eta 1. So, if we see the effective load torque seen by the motor, that is equal to TL naught into omega m by omega m here plus F1 V1 by eta 1 omega m, that is equal to TL naught plus F1 into V1 or F1 by eta 1 into V1 by omega m. So, this is the expression for the effective load torque seen by the motor when we have a translational load. So, in translational load we have to take the ratio of the linear velocity to angular velocity, which will be used for transforming both the inertia and also the load torque. Now, when we talk about load torque, we have to see what are the various components of the load torque. Now, we will be discussing about the components of load torque. So, the motor is driving a load. Let us say we have a motor which is driving a load. These are mechanically coupled. We have the motor, we have the load, the motor is running in this direction, the motor torque is here T, the load torque is opposing the motor torque, that is TL. Now, what are the components of load torque TL? TL is a load torque which consists of usually two parts. The first part is called the friction component, that is TF, and the second part is the useful load torque, that is TL. So, what is TF? TF is the friction torque, what is TL? TL is the useful load torque, useful load torque. The friction is an integral part of a mechanical system. I mean, no mechanical system is possible without friction, but the friction is of various types. The total friction torque is TF. Now, when we talk about various types of friction, this TF consists of one friction which is called a static friction, TS. Another type of friction is called the Coulomb friction, TC, and the third type is called the viscous friction, TV, and the fourth type of the friction is called the windage friction, TW. So, TS is the static friction, TC is the Coulomb friction, TV is the viscous friction, and TW is the windage friction. So, we have primarily four types of friction: the static friction, the Coulomb friction, the viscous friction, and the windage friction. The static friction only comes when the motion has not started, when the motor speed is 0. So, this is the friction component which is only present during standstill condition or during very low speed condition. So, this is present during the low speed, 0 to low speed condition. So, this friction component is only present during 0 to low speed condition. And the Coulomb friction is a friction which is independent of the speed, whether the speed is 0 or high or medium, the Coulomb friction is constant. So, the Coulomb friction is independent of speed. When we talk about the viscous friction is proportional to the speed. And the windage friction is proportional to the square of the speed. Square of speed. So, this is proportional to the square of the speed, and the viscous friction is proportional to the speed. Now, we will see the four types of friction: the static friction, the Coulomb friction, the viscous friction, and the windage friction by plotting a graph in the speed torque plane. So, we will see the various friction components. The components of the frictions are shown here. So, we have the origin here. So, we are plotting the friction component Tf, and our speed is in the y axis and the friction torque in the x axis. So, we have the friction, static friction. In the static friction, what we have here, we have the frictional torque present when the speed is 0. So, this is static friction. When the speed is 0, the torque is present. When the speed is increasing, the static friction decreases, that is Ts will be equal to 0. So, when the speed is negative, the torque is also negative. So, this is Ts. So, these are the two values of or two plot of the static friction for positive speed and for the negative speed respectively. What about the Coulomb friction? The Coulomb friction does not depend upon the speed. So, the Coulomb friction is independent of the speed. So, we can say it is almost constant, it does not change with speed. So, this is Tc, the Coulomb friction. When the speed is negative, the friction will also be negative. This is the Coulomb friction. So, the Coulomb friction is almost constant, this is independent of the speed. What about the viscous friction? The viscous friction is proportional to the speed like this. So, this is the viscous friction Tv, the Coulomb friction is this one, and we have another friction which is called the windage friction, and the windage friction is proportional to the speed square. So, the windage friction, if we plot here, this will be proportional to the speed square. This is the nature of the windage friction. So, the windage friction is proportional to the speed square. As you go on increasing the speed, the torque changes as the square of the speed. Now, when we add all this friction component, we get the overall behavior of the frictional torque. So, the overall behavior of the frictional torque can be plotted like this. So, initially we have the static friction, it gradually decreases and then it increases like this. Similarly, here in the negative side we have static friction, it increases like this. So, we have the speed in the y axis and torque in the x axis, the frictional torque. So, this is the frictional torque behavior. So, what we now see here that at rest, when the motor is at rest, we have all frictions coming to picture, static friction, Coulomb friction, viscous friction is 0 and the windage friction is 0. So, we have static friction and Coulomb friction present during 0 speed. When the speed picks up, the viscous friction and the windage friction they increase, the Coulomb friction is constant, the static friction vanishes. So, this is the plot of frictional torque. Now, friction is a passive load. So, friction is called a passive load because when the speed direction changes, friction also changes. Friction only opposes the motion. So, the definition of the passive load is this, that when the speed direction changes, torque also reverses, and those torque which reverses with speed direction are called passive load. Direction of frictional torque changes with the direction of speed, because when the speed reverses, the friction should also reverse. So, that friction will always oppose the speed. Now, with this background, we have seen the friction component of the load torque. What about the useful load torque? Now, we will see actually what are the various types of useful load torque we have in an electric drives. Nature and classification of useful load torque. When we talk about the useful load torque, the load torque must do some useful work. The first type of load torques are the fan type of load. We have the fans rotating, and these fans is useful in the sense that this is giving us the wind. Now, as the fan rotates, it also exerts a torque on the motor. So, the first type of motor is called the load is called the fan pump and compressor type of load. Now, these types of load, if you see the load torque behavior T L versus omega m, omega m is the speed, T L is the load torque, the useful load torque. T L here is proportional to omega m square. The load torque for fan, pump and compressor is proportional to the square of the speed. Now, we have the second type of load torque, which is called the hoist type of load. Hoist means we have a cage which is being lifted up. Now, there is the gravity here and this cage is being lifted up. So, we have a constant gravitational torque here, but we have two types of hoist, a low speed hoist and a high speed hoist. So, for a low speed hoist, torque is nearly constant. It is independent of the speed. So, in this case, if you plot the torque, the load torque versus speed for a low speed hoist, speed in the y axis and torque in the x axis, this torque is nearly constant, does not change with the speed. So, this is the low speed hoist, because this gravitational pull is almost constant irrespective of the speed. M g is constant, because m is the mass, g is the acceleration due to gravity. So, that constant. But if the speed increases, we will have a high speed hoist. In high speed hoist, we have the situation which is little different. This is our load torque and this is omega m is the speed. For high speed hoist, initially the torque is constant, but as speed increases we have viscous friction and windage friction. So, for the high speed hoist we have the torque profile which increases with the increase in speed. Now, we have other type of load, that is the traction load. The traction load is primarily by electric vehicle. This is by electric vehicle, locomotive, these are called traction load. How does a traction load change with speed? Now, when we talk about a traction load, the maximum torque is primarily at the starting. When the machine starts, it has to overcome lot of static friction. We have large amount of static friction. So, the traction load is characterized by a large static friction. And decreases as the speed increases. So, as the speed increases we have the windage friction etcetera, but the traction load is characterized by very large amount of static friction. So, this has to overcome the static friction and again when the speed increases the torque increases. So, this is the starting torque. Which is primarily because of the static friction. We also have other types of load. Say for example, we have power load, constant power load. What is an example of a constant power load? Say for example, we have a coiler drive on which a cloth has to be coiled. As the cloth is being coiled, the diameter of the roll is increasing. So, we have a coiler here and a material which is being coiled up is rotated, the drive is rotated here and this has a tension that is F t and this has a linear velocity which is v, and we have to keep F t to be constant, the tension has to be constant and the linear velocity has to be constant. And this has got an angular velocity that is omega m. Now, what is this omega m? Omega m is nothing but v by the radius. R is the radius here, radius of the coil. So, we can say here that F t into V should be constant, that is equal to F t is F t here and what is V? V is R into omega m. So, F t into R is torque into omega m, so that is equal to constant. So, for a constant power drive, the power is constant, power is the product of torque and speed. So, when we keep torque and speed constant, we get a constant power type of load. So, the speed torque characteristic of this type of load is the following: the speed is in the y axis and torque is in the x axis. So, this characteristic is of this sort. So, here T L into omega m is constant. So, when we say that the torque into speed is constant, we get the constant power drive, that is the P remained constant. So, these are the various types of useful load torque that we have seen. We started with various types of load, the frictional component, we talked about the fan type of load in which the load torque is proportional to the speed square. We talked about the low speed hoist where torque is primarily constant, and we also saw the high speed hoist where torque increases with the increase in speed. Then we have traction load which has a high amount of starting torque. As the speed increases, we have the friction, the viscous friction and the windage friction which also comes into picture. And at the end we saw constant power load where the product of torque and speed needs to be constant. So, we stop here for today's lecture, we will continue in the next class.